Scenario: Space Telescope James Webb discovers WASP 96b, the main infrared transmission region of an exoplanet has stunned the entire space industry. A startling revelation from the James Webb Space Telescope has revealed subtle elements that analysts did not expect. With the most accurate study to date of a planet outside our solar system, a new telescope has once again signaled that a new era of space exploration has begun. What did the James Webb Telescope find about exoplanet WASP 96b that surprised scientists so much? And could there be life on this distant planet? WASP 96b is a secret wanderer hidden in the infinite darkness of the universe. Every now and then, this exoplanet passes like a phoenix in front of its star, giving us a moment to see and explore this distant world. The fascinating planet orbits its star extremely fast and amazingly close, making its climate hellish at over 725 degrees Celsius. The gas giant needs only 3.5 Earth days to complete one orbit around WASP 96. Since its discovery in 2014, this parent planet of the WASP 96 star system has spawned many mysteries. Now scientists are beginning to unravel these mysteries with the new James Webb Telescope. WASP 96b is located approximately 1,150 light-years away in the constellation Phoenix and is believed to be a gas giant. It is about half the size of Jupiter and has a sodium-rich atmosphere. Despite its similarities to Jupiter, WASP 96b has no direct counterpart in our solar system. In June 2022, the Webb Space Telescope captured the purest feature of this distant world, fascinating people on Earth. Webb demonstrated his extraordinary ability to accurately analyze the atmospheres of distant planets. For the first time, scientists have found water in the atmosphere of this hot, bloated gas giant, as well as evidence of clouds and fog. What exactly do we know? This graph got all the scientists excited. James Webb struck with his near-infrared camera and gapless spectrograph, revealing the characteristics of the atmosphere of the hot gas giant WASP 96b with such precision that it confounded astronomers. It's like looking at a distant house with binoculars and suddenly seeing all the details. James Webb provided a complete transmission spectrum with his NIRIS instrument, the most accurate we've ever had for exoplanets. This transmission spectrum is obtained when starlight filtered by a planet's atmosphere is compared to unfiltered starlight. This type of observation, called a transit, provides the most accurate information when a planet is next to its star. James Webb creates a graph of 141 individual data points. They can be seen as white circles, each representing a specific wavelength of light. The differences are due to the absorption of starlight by the planet. The planet's atmosphere also blocks or alters some light waves, creating a trail of light around the planet. One light curve from Webb's near-infrared camera and slitless spectrograph shows the change in brightness as a planet passes a star. In the diagram, wavelengths vary from 0.6 micrometers in the visible red to 2.8 micrometers in the near-infrared region. This new technology is phenomenal. For the first time in human history, it is possible to give precise explanations about distant exoplanets. Analysts can now detect many important gases in the planet's atmosphere in patterns of light absorption. Each gas has its own light wave pattern, and Webb recognizes these structures quite naturally, providing ready-made graphs and evaluation data. After a few hours of observation, scientists can examine an incredibly wide range of data from peak heights in transmission data to interpret atmospheric temperatures. And of course we get information about important gases like water. A hotter planet like WASP 96b has amazingly high peaks in the curves and very specific patterns that reveal water vapor and clouds. The parameters of the measurement tables are variable, and the density and height of the cloud cover can even be predicted. Other graphs show the abundance of different gases and show biomarkers. It will take a lot of time to fully analyze the data from WASP 96b. But scientists were able to share 4 of the most fascinating facts about this world with the public quite quickly. For example, we now know that this world has water vapor in its atmosphere. Peaks in the transmission curves indicate the presence of clouds, and a slow decrease in area indicates possible cloudiness. Such rating curves also determine a high atmospheric temperature of approximately 725 degrees Celsius. WASP 96b is almost certainly dead. If it were a gas giant, it would probably be as unpleasant a world as Jupiter or Saturn. This detailed infrared spectrum is truly like a miracle. The reality that Webb will be able to analyze distant universes must have been intended, but the wonder of the telescope in action today never ceases to amaze the logical community. We've only been able to detect exoplanets in the vastness of space since the mid-1990s, and now for the first time we can learn subtle key elements of these distant universes. WASP 96b may not be a promising candidate for life as a gas giant, but the capabilities of the James Webb Telescope can detect Earth-like planets and signs of life. A close observation of WASP 96b was made using the SAU mode of NIRIS. SAU stands for Single Objectless Slitless Spectroscopy, and this innovative strategy analyzes the spectra of single celestial bodies without slits. This slit-free approach allows a wider spectrum of light, simplifies examination and improves the quality of data collected. The SAU module captures the spectrum over a wide range of wavelengths, regularly from 0.6 micrometers in the visible red and up to 2.8 micrometers in the near-infrared. This ability to capture a broad spectrum in a single presentation is particularly useful for analyzing the climatic composition of exoplanets. This allows scientists to distinguish the signatures of water vapor, carbon dioxide and other important particles. The James Webb Space Telescope represents an advance far beyond the capabilities of its predecessors. The amazing instrument uses mainly infrared spectroscopy, making it far more powerful than Hubble or ground-based telescopes. Ingenious technology and the ability to minimize interfering radiation will greatly advance the direct detection of larger exoplanets. The near-infrared camera system, near-infrared spectrograph, mid-infrared instrument and fine control sensor/near-infrared camera and slitless spectrograph covers an exceptionally wide range of infrared wavelengths, enabling precise studies of various planets and other galactic phenomena. Experts point out that we are only at the beginning of the study of WASP 96b, and thanks to new technology, we can expect to see completely new information about exoplanets from this telescope. Will shock us for the next 10 years. Exploring exoplanets at the edge of the modern universe seems hard to imagine, but of the estimated trillions of planets in the Milky Way alone, we've found just over 5,000 so far. These distant universes orbiting outside our solar system are an extremely difficult path. They themselves do not let light through, and even gas giants are tiny figures when they pass their stars. Launched in 1990, the Hubble Space Telescope was one of the first instruments to make precise observations of objects outside our solar system. Hubble has already given us valuable information, even though it was not specifically designed to study exoplanets. To delve into this information, scientists put the Kepler Space Telescope into space in 2009. Kepler revolutionized the study of exoplanets thanks to its ability to distinguish small changes in the brightness of stars, and since its launch, the number of discovered planets has increased. Every day per day astronomers have developed various methods to observe these small cosmic objects. The transit method, which observes the periodic dimming of a star when a planet passes in front of it, is one of the most successful techniques. Another method is the radial velocity method, which measures the motion of stars under the influence of the gravitational pull of an orbiting planet. These movements lead to small but measurable changes in the spectral line of the star, indicating the presence of a planet.